Hi, welcome to Math 5001 Linear Algebra. I'm Ryan Fidausi, going to present for Group 6 for question 1. So, part 1 of the question. If A has the point of -1, 3, 4, B 4, 6, 3, C -1, 2, 1, and D are the vertices of a parallelogram, find all the possible coordinates for the point D. So, let's go to the answer. So, there are three possible ways to arrange the 4 points of the parallelogram. I'm going to label it as P1, P2, and P3. And these are the sketches, how it look like if you're facing it from a perpendicular angle, meaning you're looking at it directly at a 90 degrees angle. So let's focus on the D because D is the missing point. So the way you can arrange it, you can put it between A and C, and then you can put it between A and B, and lastly you can put it between C and B. So there are three different combinations. So that's why we say there's three possible ways to arrange it. So let's start with P1. To find the coordinate D on P1, we can find it by finding its position vector. So position vector is the vector that originates from the origin, which is the middle here, with a coordinate 0, 0, 0. So if I draw a line, I'm going to draw a red line from here to here. That vector is called a position vector, where D is at the moment. And we can denote it as OD with an arrow on top. So that's OD. And to find it, because we don't have D, but we have A. So we can find a position vector of, we can use position vector of A. So I'm going to use a blue line. And then from A, we can go to D. And it's the same thing as the red line. So the vector that we find out eventually will equal. So that's why we denote it by vector of OA plus vector of AD. But we don't have AD. However, we can compute AD by finding vector of BC, which we have the position vector for each of them. So we do this by minusing the coordinate of C, and we minus B from it. And from there, we just add them together, and then we get -6, -1, 2. So OD equals to that, and that is the position of D in P1. For P2, we repeat the same thing. Again, now D is here. And again, we don't have the position of D yet, so we need to use the closest or anything that we have. So in this case, I use OA again, so because we have OA directly. And then we add AD because the arrow points there. But again, same case, we don't have AD, but AD is the same thing as BC. So we can reuse it. Now we get the same position vector because the equation is the same. I do want to point out that the arrow, there is something about the arrow, like the arrow doesn't matter because it's a parallelogram. I don't have to draw it, but I just draw it just to reinforce it's a parallelogram, just to avoid the confusion. I'm just mentioning this to avoid the confusion of why BC instead of CB. But we get the same point as in P1. Now in P3, the last combination. So now D is between B and C. Again, repeat the process. We try to find the position vector of D, which is denoted as OD and arrow on top. Now this time I'm using B. So OB plus BD. And again, because we don't have BD, we can use the one that we have, which is AC. And because they're the same thing, they're the same vector, pointing to the same direction with the same length, which is a characteristic of parallelogram. Repeat the process, and then we get the position vector of 4, 5, 0, which is also the coordinate. So this is the question, and the answer is point D can be either -6, -1, 2, and 4, 5, 0. And it's because there's two same vectors, position vector. Now, Now, coming to part 2. A parallelepiped is a generalization of a parallelogram in the same way that a cube is a generalization of a square. In other words, a parallelepiped is a 3D object whose sides are parallelograms. Now, let 4 points on a parallelepiped be O, 0, 0, 0, A, 2, 4, negative 2, B, 3, 6, 1, and C, 4, 0, negative 1. Find the other coordinates of the parallelepiped. Now, the first thing I'm going to do is first a description. A parallelepiped has 8 points. The same thing as a square. A square is a special type of parallelepiped actually. All the angles are 90 degrees. So it is a special type of parallelepiped. So given the 4 points, we can construct 4 different ways, 4 different parallelepipeds from the points. It's the same concept with the previous part of the question in part 1. There are different combinations how you can arrange the points. So step 1, I'm going to plot the points that we have given in an R3 plane. So as you can see, I labeled the x-axis as the scaling is half of this diagonal square is 1 unit, 1, 2, 3, 4. And the y and the z-axis are 1 unit each per square. So for example, well, origin's in the middle, 0, 0, 0. To find A is 2, 4, negative 2. So go x-axis by 2 units here. And then y-axis by 4 units to the right. 1, 2, 3, 4. And then the z-axis by 2 units going down. 1, 2. So we end up here. And I repeat the same thing for the other, for the B and for the C. So just showing C, for example. 1, 2, 3, 4. So it's 4, 0, 1. So we're not going anywhere on the y-axis, and then going down by 1 unit on the z-axis. So we end up here. So that's step 1. Step 2. So because a parallelepiped has 8 points, we need to find the 4 other points. So step 1, we done it, plot the points, and then step 2, we're gonna sketch vector lines from point O to the other 3 points to form edges of the parallelepiped. So we're gonna call this first parallelepiped PO, and I'm gonna call it by just the short notation like PO, PA, PB, PC, and so on for each parallelepiped. And then we do the same thing for PA. So we start from A. Oh, for example, I'm gonna explain PO first. Here's the origin. I just draw lines with different color heading to the different points A, B, and C. Now same thing I did for A, starting from A and then heading to B, C, and O. For PB, starting from B and then draw vector lines heading to A, C, and O. And then the last one is PC, parallelogram that starts from C. Vector lines again to origin, to B, and to C. And now we have 3 edges of the parallelepiped. Now the first one, PO. So we did this, and then from here we can construct a parallelogram, and it needs a bit of trial and error and some imagination. So you're gonna imagine sometimes it's quite clear, but sometimes they're a bit hidden. So we have to try and error to construct it. So what I did is I choose a vector, a starting point, and then I just add the lines. For example, this blue line, I just add them at the end of the other vectors. So for example here, I just add a blue line, and I add a blue line here as well. And because I know there's gonna be 4 of the blue lines at least, but I'm missing the last one, so I need to try construct the other edges. So let's choose an orange color. So we have already 1 line, so we need 3 more lines. So I'm just gonna add the other edges. And somewhere here. Okay, so we have 4 orange lines, so that's a good sign. So now we need the purple line or the pink one. So it's heading there. So I assume it's gonna link here, and then this one links up here, and then this one links up here. Oops, missing a bit, but you get what I mean. Oh no, that's a mistake. Um, this one links up here. So now we can finish the last blue line that we did just now. There you go, parallelepiped. So that's the same diagram here. Now we repeat the process as what we did in part 1. To find D, we use is equal to the position vector of OD, vector OD. And this can be computed from the position vector OB. So I'm going to use a highlighter this time. Let's pick a color. Green. We don't have a green. So we start with OB, which we already have, 361. And then we want to head to D, but we don't have D. But remember, they're the same vector as OC. So, and OC happens to be on 4 or -1, which is also its position vector, which is also its vector. So we can add directly. So we get 760. Repeat the same process for each point, and you'll get all 4 coordinates. So just a sanity check, let's try finding like the answer that we have on D, for example, 760. Let's see if we got the same the correct point. So 7 means we're going down by 7 units on the x-axis. To, well, depends how you see it. I'm just gonna call it down because we're heading kind of down. 1, 2, 3, 4, 5, 6. And then going on the y-axis by 6 units. 1, 2, 3, 4, 5, 6. And then lastly, oops, round off. I think I made an error somewhere. So first going down by 7 units. 1, 2, 3, 4, 5, 6, 7. So it's here. Yep. Okay, got it. And then on the y-axis by 6 units. 1, 2, 3, 4, 5, 6. And then on the z-axis, it's 0. So we're not going anywhere. So we end up here. So I did the same thing for each point, just as a sanity check. Now that's PO. Now we repeat the same process for each P. Now for PA, again, same process. I start with the 3 edges, and then I try to construct the parallelepiped. Took some trial and error, but you'll get it eventually. Same process what we did. Same thing what we did in D, E, and F, and G in PO, and you will get each point. And then again, I'm just gonna check randomly. For example, G. Point G is 5, 2, 2. So let's start from the origin. Going on the x-axis by 5 units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, somewhere in the middle. And then going to the right on the y-axis by 2 units. 1, 2. And then on the z-axis going up by 2 units. 1, 2. So we end up at G. So that's the thing in the RTU plane. It doesn't intuitively tells you right away by looking at it. You actually have to go through this skipping the line, like jumping lines process to end up at the coordinate. So that's PA. PB, same process. It's getting a bit repetitive, but here you go. Starting from B, draw 3 lines and then construct the parallelepiped. And it gets a bit more complex, like the shape is not really straightforward as the previous two. But again, it's the same process anyway, try and error until you get the shape. Just check, for example, F 162. So 1, and then go to the left by 6 units. 1, 2, 3, 4, 5, 6. And then on the z-axis by 2 units. 1, 2. So end up there. So F. There you go. And you can check the other points if you want. Same thing for port C. I'm not going to repeat it, but you get the point. So we get D, E, F, and G. And same process I did from start to finish. So back to the question. Find the other coordinates of the parallelepiped. So for each PN, we share the same 4 points. And then these are the other points, D, E, F, and G. And these coordinates correspond to the points. There is another way to do it, but I did not show it here. It's without sketching, but I find for this kind of question, visualizing it is the best. You can also write it down and just do the calculation, like just from the 4 points, you know there's other points, and then you can work out there are 4 different combinations. You can arrange the 4 points to get the other vectors, to get the other points, sorry. But I find visualizing is the easiest one because you get to see where it is, and there's also the check process where you can check your answer at the end. Anyway, that's the whole question. Thank you for joining, and I hope you have a good day. Bye.